in the original, we were to open up the half-hull model, which we already have results computed, and open up this model and take a quick view at our deformed result. And we're just interested in the sagging and hogging to see which one has more deformation. So if we come in here and look at the scale factors, we can see the sagging case had to be multiplied by 53.5, and the hogging condition was multiplied by 86.6. So it has a greater magnification, which means our sagging case had the larger deformation. So we'll focus on this case to run a couple of fine mesh models. So let's say something we might want to investigate might be, say, this girder connection. Now this is a realistic design here. We've got a deck ending on a fairly poorly stiffened bulkhead. But if we wanted to see what that frame connection might do where it hits this vertical bulkhead, we can create a fine mesh model where we convert it to quads and see what exactly happens there. So let's do that. We'll create, come down another frame data here, and we'll also take, let's say 2 days ago, and just go one forward, because we're really just interested in that connection with the hull. So we'll use that as our call this girder end. We'll create that as our general group for a test case. Let's go ahead and refine that. We'll start off by making a top-down version of this. We do want the girder to be converted to quads. We can go ahead and leave the flange of the beam. We're not too worried about the stiffeners. And we'll use the default, which will do 5 elements per single deck element there. And while we have this created, let's come into the parts view here. You can see we have our new module. If we check the location of the origin, you can see for that newly created fine mesh module, or origin is at the global origin. If we view our original model, you can see if we use view all, we can see our fine mesh module overlaid on the global. And make it run a little faster, we'll come in here and we will delete everything but the sagging case. This is further top down. Let's go ahead and run this. We'll solve both the global and the fine mesh. Let's just take a minute to run. And actually, even in the deformed model, you'll see that when we do the view all module, we can see both of the models overlaid and compare the deformations between the two. It's a little more difficult to try and do stress contours when they're overlaid with each other. Normally, we would be looking at the one model, and you can see in this bulkhead, we have fairly smooth bending of that plate when it was just a standard beam element being used in the model. When we look at the fine mesh version, still very smooth, but it looks to have a bit more curvature there. Now, part of that is just the resolution of our global model. We only have 1 meter resolution between points, so we're not going to capture a lot of curvature there. And if we view all modules, see if we can notice something. Let's try and so we can see there's a little difference in the deformation when we run with the finer resolution there. But again, this is amplified, and that is a very poorly designed bulkhead. So let's look at the stress contours now. If we just look at the one we see, if we look at our global model, everything is in a pretty low stress range relative to the peak in that area on the global. When we look at the fine mesh, we have a more refined scale at this point, so you can see exactly where the stress concentrations are. That vertical stiffener at the sort of hinge point for that beam is taking a substantial load. If we use this value, let's scale our full ship results to 7.29 e to the 7. So we can set our range. Make this just see, as expected, we do get much more refined results. And we can run the same analysis if we say delete this fine mesh module, and we will come in and create the embedded version. As I was saying earlier, with the top-down, if you were doing evaluations of a lot of different options for different areas, say the frame-to-frame connection, say different options around openings, you could have dozens of these fine mesh models throughout your hull, and if you were to embed them, each option would require a separate model, and whenever you ran, you were still in the design phase where you're modifying things on your global model, it could substantially slow down your run times. The top-down version, you don't get, I guess, as tight an integration because you're solving the global first and imposing that on the fine mesh. But you can save a lot in terms of runtime if you have a lot of them throughout the model. Information, we get a similar result to our top-down version. Although here, we only have the one option for viewing, since it did replace portion of the model. Fairly straightforward, and I guess the use cases would depend on whether you'd want to use the top-down or the embedded, what refinement levels and things like that, depending on what your goals for the fine mesh version. But the mechanics are fairly straightforward for how to create them. Now you can see when we created the embedded model, didn't keep the group, but when we did this, it destroyed the original group that we had used to create the fine mesh model. Whereas when we ran the top-down, that group was still available and could be reused for generating different versions of the model.